All right, so welcome back to this channel. So in the last video, I think we have officially ended the variational autoencoder section or series. So in this video, we are going to start off a new series or new model. It is called stable diffusion, right? So it is you might have heard about that. You know, there has been like a lot of hype around this model in this time. I think probably before ChatGPT, yeah, in the field of deep learning. This is like a huge hype. Using this, you can actually generate like new images and very realistic images. Like you could add like very um, metaphoric prompts, and then you could get like very good results, right? So that is stable diffusion. Again, stable diffusion is a language model. Sorry, not a language model, generative model, image generation model, which can generate new images for you, and then you can even text like input the text, and based on the text, it will output your image, whatever you want. We are going to, in this video particularly, we are going to discuss the theory, and we're just going to look at a demo of like how it works. I'm going to first start off by the demo, just to make sure that you are excited, just like I am. I like We'll be going through a lot in this series, so this series might be a little long because there has been like a lot of papers and a lot of techniques in this field. uh, by saying long, I mean like maybe like 5 6, like comparatively, compared to like VAE, we'll be having like a very compared to VAE series, we are going to have like many more videos. So let's get started. Let's first get started. I'm going to get you to this notebook called stable diffusion demo. Again, all the notebooks will be in the probably for this series. I'll probably create a repository, right? I'll put the link of the repository, the GitHub repository on in the description. So just like all the notebooks and maybe all the resources, I'll put there. So just check that. So first, right, let's just go through this code just to make sure that you understand like what is stable diffusion. We're going to use the API version, right? So first, we're going to import the model, the diffusers model. It's like a library. You could actually access it using like a simple API call or just simple function call, right? I'm going to run that, and I have already run that. I have run both of these cells because they took like some time. All right, and then we're just going to install them, and again, and then this next cell, right? In the next cell, will import some more libraries that we'll be needing. Right? We'll be needing logging, we'll be needing path, and some more libraries. So this is the stable diffusion pipeline. So from the diffusers that we have just downloaded in the previous cell, from the diffusers, we are going to import this function or this method, stable diffusion pipeline. And then we're also going to import like concatenation and notebook login. Again, we are going to use a Hugging Face model. So therefore, we will be needing a like ABI key. So if you don't know about Hugging Face, then Hugging Face is like a large um, community, online community, where people build, develop, and train their models. When like every model they train, they will just put up in the Hugging Face community, right? You can just access like whatever models, right, you have. And so what we'll be doing is what I wanted to do is go to something called Hugging Face, just type Hugging Face and probably log in, something like that. Click on that, and then I have already logged in. So if you haven't logged in, if you do not have an account, create an account, sign up, maybe with your Google, maybe with your Google account. I don't care. Just sign up with anything, right? And then you'll get a this page. Just click on this button. Just click on your profile. You can just access your profile. Click on settings, and then here at settings, click on access tokens. And if you click on access tokens, you'll get a key. Just click on copy, and you can just get the key. After that, just run this file, and then you'll get a prompt. You'll be asked for the token. Just type the token, and you are ready, right? We will be logged in once you have entered the token. So what we'll be doing is we are just going to like disable login warnings, right? And then what we're going to do is we are just going to log in. We're just call this function called notebook login if we haven't logged in already, right? And then now I'll run this to actually get the pre-trained model, to access the pre-trained model. It takes about 1 minute to run this cell. So we'll just say stable diffusion pipeline, the one that we have like important above. We call that on from pre-trained on this like this is like a model file or the name of model, and then we could just call that. So we will just be loading this model for our use for using it here. So version v1 4 whatever that is. Now now we can actually use it. Now we could actually use this stable diffusion API, right, to actually generate our images. So I'm going to create a prompt. I'm going to say a photograph of a motorbike rider sitting on a car. I mean, yeah, like that is a very weird comparison, but you could add as many crazy things as possible, but it is going to generate an image because it does it because the model can understand what is a motor bike and then what is a car, right? And then it could understand every word, and it also could understand how images look. So it is hopefully it is going to generate as a new good image. So we're getting this error. I'm going to layer let's just search on like let's just search this error on Stack Overflow, like how what that is. See what's up. Right, so let's see what we should do. I think we should add this. It should add it. No, I don't think that is how we should add it. But maybe I'll run this. I'll get them with that. Let's see. All right, we're getting the same error. I'll probably put that above. All right, hopefully it works. No, again we're getting the same error. Right, we're getting the same error. Layer column implementation. But I'll just pause the screen recording. I think I'll probably try to figure something out. All right, so yeah, so I have made some changes. I'll just show you what the change is. Just ignore this cell. So the reason why this code does not work is because we have to use a GPU to actually do this. I think that is a problem. So what I want to do is when you are running on Google Colab, just go to runtime, just click on change runtime type, and click on GPU, select GPU, just to make sure that you are using a GPU, just to make sure that things are fast. All right. Right. Okay, I have to run everything again. Okay, it will be good. So what I want to and the next change you have to do after selecting GPUs in this line when you're calling create this pipeline, when you are creating this pipeline, when you're just initializing this pipeline to actually use it. After at the end of like calling this like function or creating this pipeline, just add this small statement dot to and specify CUDA in there just to make sure that you are using a GPU. Right, so I have run this with this prompt, and you know I have got a rather absurd output. So as you can see, you know, like it does not seem like a car, does it? And even he does not look like a motorbiker. You know, the way he's sitting there. All right, so that okay, yeah, we got an output, and let's just change it and maybe run that again. A photograph of something, maybe something less ridiculous, something like maybe astronaut riding a horse. It's a very good example, very famous one. Run that, and you'll get this processing. It'll probably take like 15 different steps, like 50 steps to actually do it. And yeah, you get some amazing images. I will run that again the final time. Then I'll get a new image. Yeah, 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 good image, right? Yeah, the images are pretty good. Probably the model has a problem with faces. I don't know. So, and then what I wanted to show is I think this model ran for 50 inference steps, right? This when like using this for inference, uh, we have to specify the number of steps we want to like update the model. For example, when you input a prompt, the model will generate like first image. It will generate the first version, and then it'll like for 50 times it will update the version, and it will generate new versions. Increasing the realness of this image. And then if you do it for like 3 inference steps with the same prompt, you'll get images like this, which you definitely don't want, right? You don't want images like this. So yeah, they seem pretty pretty bad, right? So at the third step, you will get images like this. And if you run for more inference steps, you could like this is actually a parameter. You actually use it to actually determine the number of inference steps you want the model to run for. So make sure you increase the inference steps while actually using it. So that is like one thing. And then the second thing I want to show you is the like is the ability for you to actually subtract things. For example, I'll just show you what that is means. So I'm first setting a manual seed just to make sure that you and I will get the same image when we are running this. So we'll set a seed such that we'll get the same image and there is no randomness for us. And then even for the future use. So if you run this, you'll get an image. No matter how many times you run this, you are getting the same. You are going to get the same image because we have set the seed. And then I'm just going to call this statement. Sorry, Labrador in a style of Vermeer, right? And then you'll get image like this. Now what we can do is I can just call the same prompt, but I can say that negative prompt equals blue on the same image. I'm going to this first image as the same seed. I'm going to negative prompt blue. So I'm going to remove the blueness in this image. So I'm going to get an image like this. Yeah, the blueness in this image has gone, right? We're going to get something like black. And that is the good thing of stable diffusion is you could actually, the model is so good that it actually can remove and add features, right? I mean, yeah, this is blue and this is not blue, right? Just not blue. All right, so that is one thing that might be like pretty overwhelming for us, like pretty good, pretty fascinating. Now other thing is we could also do image to image translation. We could taking an image and translate it into another version. I'll just show you what that is. Right, I'm going to import the other method. So from the diffusers function that we have downloaded previously, we're going to import another method called stable diffusion image to image pipeline. And then also going to import like fast download to actually download an image online. I'm going to call this stable diffusion image to image pipeline, right? This version, and like we're going to set some parameters. Sorry, I'm going to stop it because we have to do the dot CUDA, right? Because otherwise we might get an error saying that runtime error. Maybe we don't have like enough computational power. I'm going to run this. Just ignore the warning. It means nothing. Might take some time. Meanwhile, I'm going to run this. So we're going to download the image from this link. So opening this link will just get to the image. So we're going to use this function fast download, and you could use it to actually download I think any images. Maybe you can just call this function dot download. This thing crashed. Right, so I think do you have to rerun it? I think I'll run it again. Right, so I've put my key in there. I think we'll run it. Rerun everything. Rerun everything. So yeah, it might take some time because of course, like we are loading like huge models. So these are like huge models. It is stable diffusion is like it probably took like many hours, not hours. probably days or even weeks to actually train in mini GPUs, of course. Um, and they will even be needing that. I'll just stop it. We'll run the required part that we actually need. I'll run this part because we are currently dealing with image to image translation, right? Hope you understood about the previous things, how to actually generate new images from prompts. Now here, this is about image to image translation. We are going to load the model and take some time, but we'll wait because waiting is a like something that you should learn as a machine learning engineer, because when you're training the model, might take a lot of time. So meanwhile, I'll just go through the next code. So we are going to build this function called image grid, which takes in the images. So when we in the succeeding cell, we are going to build like print like multiple images. So therefore, we'll be needing this function. We'll be taking all of these images. We'll be like creating rows and columns. Right? We'll just create like a rows and all that. Why is this not working? Access denied. Right. I'll just try to load up any images online. Maybe um painting, drawing, maybe something like that. I'll copy the download link. How can I copy the image link? I'll put the link here. Maybe it does. Hopefully it works. Maybe it doesn't. We don't know. Right. So we got this image from online. Now what we'll be doing is we'll be printing another prompt, maybe something related to this image. So what we'll be doing is I'll probably change this prompt to something else. Maybe uh, two kids playing in a sunny day, 4K, something like that. I'll probably run this. Let's see what image we'll get. Might take some time. It'll definitely take some time because we'll running like 15 different steps for like each image. So let's see. And then we like the prompts here, num images per prompt. So we are going to get 3 images for each prompt here. And then the image, we are going to set the initialize like initialize image. What? So we're going to set the initialize image, initial image as this image, right? Yeah. Okay. So these are the outputs we have got. Yeah. Again, pretty, pretty, pretty weird, but still they look pretty good, don't they? Or all about like we'll run this now. And if you think about it, generating it from like a painting is actually pretty good, right? Generating a pretty realistic image from just a painting is pretty good. Let's see. Yeah, good, not bad, not bad, right? Still doesn't look like images. Maybe the model has like problem with uh maybe realist, like maybe humans. It cannot. it is not able to generate humans from like until now, right? So now I think we'll just cover up theory of stable diffusion pretty fastly. I'll try to cover the basics from like or maybe we'll do it, or maybe we'll elaborate on this function, or maybe uh, stable diffusion maybe in the next video. But I'm just going to go through the theory, right? So this is I'm going to use my whiteboard, right? So until now, right, we have looked at the demo of stable diffusion. What stable diffusion is? Again, if you want to experiment, you are more than welcome. You are more than welcome to experiment. Just go to the description. I'll provide the note. I'll provide the GitHub link. Download the required file that you want to work with, and then you could maybe run it on your own computer or Google Colab. Use Google Colab, right? So until now we have discussed about stable diffusion, right? We have not discussed, but we have looked at the stable diffusion, what stable diffusion actually is. So uh, the basic idea of stable diffusion is again image generation. So we are going to generate images either from prompts or from or nothing, or given a data distribution to actually we could use stable diffusion to actually generate a new image new image that seems to be coming from that same distribution. So that is goal, right? How can we build a model that could actually uh, make make us humans believe that it is actually from that data distribution? That is a basic idea, right? So what if, until now we have learned about generative adversarial networks and variational autoencoders for generative models. How can we do image generation using both of these models? And we could also use like text to image uh, uh text to image models, or even on generative adversarial networks we could even use GAN networks and provide it some text and maybe have some embeddings, right? We could actually input the embeddings for this neural network, and we could and also the latent vector, we could input both of these into maybe a convolutional model and probably maybe do some reshaping layers and all that, and we could actually get the output. We could also do image text image on generative adversarial networks, just so you know, I'm telling you. So the idea of stable diffusion is actually pretty similar. uh, let's let's talk about a problem. Let's talk about the happening. Okay, so let's talk about let's just think about for example in this case, let's to actually learn about stable diffusion, let's take an example of recognition, maybe MNIST digit recognition or not recognition, predicting a new digit. For example, we have handwritten digits, right? So we have MNIST data set in which we have like many handwritten digits, like in different wrote in different sizes, different shapes, maybe, right? Like that. And, even 11. I think let's just care about take 10 up to 10 digits, and we'll have like many images for one, many images for two, at different wrote in different styles. So let's say we want this stable diffusion model just naively predict or draw an image or generate an image that seems to be a digit. There is no need for this image to belong to each class for now. In this for this video, let's assume, or let's make the stable diffusion model predict an image that seems to be like a digit. It does not have to be from each of this class. So we are essentially going to be concatenating all of this data, and we're going to train the model on all of this data, and just to make sure that it seems like a digit. We just want the model to actually make it seem like an image. So how will we do that? I'm just going to cover that, but just wait a minute. I'm going to zoom in, right? All right, so let's see how that works. For example, if you look at generative adversarial networks, what will you do? Well, we just have a CNN model that predicts an image, let's say, and we could just taking this image to a maybe a adversarial network discriminator. Will give that to a discriminator and predicts how good or bad that image is. Maybe probability of how good that bad image is, maybe 0.90 or 90%. And based on that, we'll reward this CNN and maybe update parameters. That is the architecture we have used in a generative adversarial networks. But what will we do in a stable diffusion model? So if you think about it, right? For example, let's say you have an image with like lots of noise in it, right? Lots of noise, lots of disturbances, maybe a small 2 written in there, right? How could we actually make the model to actually predict the 2 from this noisy image? The basic overall idea of the stable diffusion model is actually taking a noisy image and training the model on a specific data. For example, if you train a model on digits data and give it some noise, it should be actually make out this image or any digit. It should be able to actually make out a digit. For example, let's say there is a kid. Let's say there is a small kid, and the kid has, for example, he is from another planet, or probably maybe you have a human from another planet, and you get the human and maybe teach him how a dog looks like basically how a dog looks like, and maybe like if you have observed, you know, maybe when he looks at patterns, or best example is actually clouds. When you actually look at clouds, you can actually make out some patterns of humans, let's say, or even like dragons and all that. That is because you know about dragons, you know how dragons look like, and you know how humans look like, and based on the cloud image, maybe you will be able to like generate some patterns, find some clusters in there, find some patterns that may look similar to you, maybe like a human face and all that. So that is the idea. So given this noise image, we should be able to predict the actual image, or deeperly, we should be actually predict what is the noise that is actually added to this image, and how can we actually subtract this noise, or what noise should we subtract from this original image to get a nice pattern that looks like it belongs to the distribution of the training data. So that is the idea of stable diffusion. So when we are training the model, so in stable diffusion, when we are training the model, for example, we'll have many numbers, let's say 2, 3, 1. We have many numbers, right? Many distribution, many classes, many styles and all that, many classes, but we're going to concatenate them because we are dealing with the like general problem. So what we're doing is we'll be taking each image, for example, we'll be taking the 2, we'll be adding like some noise, right? And we'll send that to a neural network. And this neural network is going to predict, or the output is going to be. So essentially, while training data, when we're actually creating the training data, before training the model, before training a neural network, what we'll be doing is we'll be taking this image. I'm going to expand. I'm going to increase the size. Something like that. Yeah, good. So what we'll be doing is we will be taking an image 2, let's say we have an image 2. We're going to add some noise, and we're going to get an image like something like 2. And so this is the training phase before training our model. This is how we prepare our data. So we'll be taking this 2 image from the training data set that we have already collected, maybe from the MNIST. We're going to add a noise, randomly generate a noise, and this is going to be the input image for the training the model. So this is going to be input, and the output is going to be this. This is going to be the output. So while training, this is the data pre-processing, by the way. This is going to be the X, and this is going to be Y. This is a unsupervised learning problem, right? So we'll be taking this 2. We're going to add, let's say, little noise. We're going to get this output image, and we're going to make this as the input image for the model. and then we're going to make this noise as the output. So we want the model to actually take in this noisy image, a very little noisy image, and predict this noise. And that is what we want the model to actually do. So if you think about it, and maybe you have something like 3, and you have like maybe many like so much loss completely randomly, or like many loss, many like you have like random noise, and you're going to get a pretty noisy 3, right? And the model is going to take this input, and then even though like you might see 3, and maybe you might have not seen 3, the model is going to make out 3. The model is actually going to predict 3. Sorry, the model is not actually going to predict 3, but it is going to observe the 3, and it's actually going to predict the noise. I don't want to confuse anything. It will predict the noise, and we could actually subtract this noise from this input to actually get this original image. So we will just subtract the both of this, and we'll get this image. Understand, right? So we'll actually take in this noisy image while training. This is how we train the model. We take each image, we'll add random noise to it, and then we'll get this input. So the input of the model is going to be the output of the addition of the actual image and the noise image, and the output of the model is going to be the actual noise. So the model is actually going to predict the noise, and then we're going to subtract the noise from the input image the model has got. In the inference time, by the way, where right, in the inference time, where while we're actually training the model, we'll get like completely random noise, like completely something like that, and there might not actually be a 2, like completely, like probably something like that, right? And then given an image like this, we are going to take it to the like stable diffusion model, STB or DF, STB-DF, right? Stable diffusion model, and the model is actually going to predict some noise, many noise. The model is actually going to predict the noise that you have to subtract from the input image. This is the inference time, by the way, when you're actually using the model. This is the inference time. And then if you take this image and subtract both, like if you take this image and subtract this noise, then you probably get a something like that probably looks like a digit. Maybe this looks like a digit, maybe it does. And you have seen like stable diffusion is like not completely accurate, but it is doing it will do pretty good. So if we'll subtract the predicted noise from the actual image or the actual noise that we have got, you will get this output. So the model is going to train to actually predict this noise. So it is going to make out some patterns inside this image. It is not completely going to depend on the noise, but also it is going to completely depend on like the training process. At the training process, we are going to also increase this noise. So maybe at some point we are going to get some 5 and maybe completely noise. We're going to get this as input, right? At some point, at least at some point, when we have maybe randomly use like so much amount of noise, and then you'll get like so much noise, and maybe you don't even see a 5 there, but while training you're going to predict huge noise. So therefore it helps the model to actually train to actually predict patterns, to actually look at patterns from completely noisy data. So that is the basic idea, the overall basic idea of stable diffusion. And to actually build a model that takes this input noise and predict the noise that you should subtract from the input noise, we are going to use UNet model. We're going to use a UNet model. We're going to take in this noise, and we're going to predict the subtract noise that we have to subtract. So therefore, I'm going to show you our architecture of how the model looks like. So we're going to slowly decrease the size, and then we're going to have like transpose layers. Actually, rebuild the model. So we are going to reconstruct this noise into something that is more that after subtracting from the input image, that looks quite like a digit in this case, at least. So like this is going to have like a lot of parameters. These are CNN layers, by the way. I might confuse you. UNet is a model. If you don't know about UNet, then make sure to check out maybe a video I probably discussed about UNet. I think in the where have I discussed about UNet? I'll probably share the link of this video where I discussed about UNet in the description. check that out. Or maybe I'll in the future I'll make a separate video, because you don't have to search for it. Right. So this is the architecture. So we're going to take in the NOS. We're going to have a bunch of CNN layers. These are CNN. These are normal CNN layers, and these are CNN transpose layers. I have told you about CNN transpose also, right? So we're going to have a bunch of these layers, and we're going to keep on updating every weight. Each layer is going to have like many weights, and then we're going to update all of these weights. So, and these weights represent the understanding of our model, right? And after like updating these weights for long or a long time, we are going to get some like good results from complete noise. We could be able to generate like pretty good images. So that is unit model. And then so this is, I'm just going to summarize what I've told you. We are going to take in some noise. So while training before like training the model, before training the model, we are going to take in each image from the training data set. So from the data set that we have already have, right? We're going to have a bunch of images. I'm going to only take 3 images now. We're going to add a bunch of noise. For the first image, maybe we add little noise. Maybe we get something image like this. And remember, we are going to have like many different tools and many different images. So therefore, it helps the model to actually learn, to actually diversify its understanding. Maybe generate like, maybe take in complete noise and predict that image. And now maybe have like a little more loss, or noise, a little more noise. Now we're actually going to get a little more noise image, but there is going to be one, right? Something like that. And maybe here we have like complete noise. And you will have this noise for 2 also. It's not that we are taking in a ascending order or anything, right? And this also will be complete noise, because 3 will not actually be seen, right? We'll have like complete noise, and maybe we have 3 somewhere, right? And from this, the model will actually be able to learn more. And then right, so this is the architecture. This is how the architecture of the model is actually going to be like. So this is how we are actually going to train the model. And then, just like a CAN model, we are going to predict how realistic that image is, right? The noise, we are going to use the model for predicting the noise, and then we are going to have a model that is going to predict how like how how much of a digit that does that output result after subtracting the output noise from the input noise. How realistic is that really resulting image is going to be? How or how much does it look like a digit? So that is how we are going to train the model. So that is the overall summary. Again, hope you understand. So after pre-processing like this, we are going to take in this input. These are all inputs. So these are inputs, and we're going to have like multiple number of them. These are all going to be inputs. We're going to input them to the stable diffusion model, and the model is going to predict the output noises. So the model is actually going to predict this. So the model is actually going to require to actually predict this. What we have added to these original images. The model is actually going to predict this. So this will be the Y, and this will be the X, the inputs and the outputs. So the model is actually going to take this image. The unit is going to take this our inputs. These are going to be inputs, and it's going to predict these noises. So that is the idea. And again, because we have like multiple images, many images, right? So we have like many images, right? We're going to have 2, and we're going to have like multiple noises to every class, or every image in that class, and for every class, we're going to have like many images. So therefore, what we are going to do is we are going to use autoencoders, right? I have explained about autoencoders, and it is useful. The concept is useful for now in this lecture, or in this state of the art, or in this field. In this stable diffusion, what we are going to do is we are going to build autoencoder through which we could actually compress the image, right? So we'll just compress this image. Sorry. So what we'll be doing is we'll be training an autoencoder that takes an image and compress it into a very small image, and we're going to have like we're going to reconstruct it, right? So we're going to what we're going to do is we're going to have architecture like this. So these arrows represent like tensor propagation or wait output propagation. So just don't get confused, right? So what we're going to do is we're going to taking this two and perform multiple CNNs and decrease it to a latent vector, decrease it to a very small vector. So we'll represent this two in this latent vector, and we're going to have a bunch of other layers through which we could actually regenerate this two. So this is called the encoder. This is called the decoder. So the encoder consists of a bunch of CNN layers, and the decoder also consists of a bunch of CNN layers. And then we're going to use these CNN layers on these two, right? And then we're going to slowly reduce the size of this output image into this dimension, this latent small latent vector, or into this small latent vector that holds all of this too. And we're going to here the decoder's output should be the same image. So the decoder's goal actually going to predict the same image. In the loss function, for all of these layers, or the loss function for the final layer, and of course it is going to affect all of the previous layers also. So the loss function is actually going to be MSC between like x, y, and x. Y minus x, or y and x. So we're going to perform like mean squared error between y and x. So therefore, we want the output of the decoder to be similar to a input of the encoder. Why is that? Because we want to reconstruct this image too, and this latent vector will be a representation of these two. So through this model, we could actually represent all of the features of this image too, or this image, not two. We're going to take this image and we're going to represent it in this small latent vector. So therefore, when we're actually training the model, rather than training the model on these images, we are going to train the model on this latent vector for this two. So we are going to pass. So first we are going to train this autoencoder. First we are going to train this autoencoder on multiple images with this loss function of mean square error between y and x. We are going to train this autoencoder on multiple images, and after training, we'll just pass this 2 into this autoencoder and get this vector get this vector, this latent vector. So this is going to be that latent vector, and we're going to do that for all of the other images. Let's say 3. We're going to pass that through autoencoder. We're going to get this image. We're going to take another image. So these are images, by the way, not just digits, not just like digital representations, actual images. And we're going to pass all of these values into the unit to actually train the model. And of course, we'll add the noises and all that. So these are like images, input images, and we'll after adding noise also. So we'll be adding noise and then passing them to autoencoder. So we'll have the noise. Don't worry, right? Sorry for my poor representation. So we'll have like, right? Just to make sure that to decrease the size of this image, right? To decrease the size of this image, we are going to do that. Pass that through autoencoder, and we're going to train the unit. We're going to pass that through the unit, and the unit is going to get trained to actually find patterns in these images. So that is the overall high level definition. I think there is a lot more to learn for us. I think that's just like the basic introduction for stable diffusion. I think this is a pretty good introduction. So in the next video, we're going to cover some more topics, some more theory. And after that, we'll be maybe going through some code. We'll be going through some code. And then, yeah, we'll be learning some very cool things. So yeah, that's it for this video. That is stable diffusion, and I'll see you in the next video. So please stick with me.